with the problem of actually counting the number of microstates for the simplest system that you can think of. I mean, the simplest system you can think of is one particle in the box, but you can add more particles to the box, right? Classical particles, there is no funky quantum business yet. And we will show how to calculate omega of NVE for this system. This will give you a sense of how it works, and you will be calculating this again and again, many times. We will show why. So the choice of delta E, which we wrote earlier, it does not matter. We will show once we write down omega, and we won't do a general proof of why delta E does not matter, but we will give you a feeling for why it does not matter by looking at a non-interacting system. From this, we will move on to a canonical ensemble. The idea being that you can't do much with an isolated system, because if it's isolated, well, you can't do much. It's locked, right? So you want a system where at least you can make some, you have heat going in and out, and it comes to thermal equilibrium, right? And later we will look at other ensembles of the same category. So canonical ensemble is a system which is coupled to a thermal bath. For this, we will derive the equivalent of omega NVE for canonical ensemble becomes Q of NVT. So just like we had S of NVE and A of NVT, we have omega of NVE and Q of NVT. And you will see that just like S played a huge role in connecting thermodynamics to omega. So the connection of microcanonical ensemble with classical thermodynamics was through Boltzmann's entropy. You will see for canonical partition function, the connection is through Helmholtz free energy. And that's what we'll look at. And definitely not today, but next class we will start to think about how to get fluctuations out of canonical ensemble. So someone asked me last time, why do I use this variables NVE or NVT all the time? Why don't I just write omega or Q? For now, yeah, if I write omega, you probably know I mean omega, the function of NVE. When I write Q, you probably mean NVT. But some books use Z for Q and Q for Z, and it becomes confusing. So it's best to keep writing the symbols, the function, the variables that you have. Yeah, your students are 1, 2, 3, 4, 5, 6, 7, 9. Where did Sumin go? Do you know, Vanessa? Or you know where is Sumin go?
She's at home.
Huh, maybe she thinks it's too easy. Give her a okay pop quiz or something. No, not for you. I mean, then it's punishment for you for being here. It's terrible. So let's try to think about N particles. And I want to stop at 12 o'clock today because this is new material. It will be a bit like, wait, what's happening for many of you or most of you? So we'll gradually build up. So N particles in a box, and let's say it's a cubic box. Of volume V. Okay, so these N particles, they are completely independent, or they are known as non-interacting particles. So the way statistical mechanics works is we will do everything for non-interacting particles for a while. And then you'll be like, what's the point? I mean, clearly, life is not made up of non-interacting particles, right? Everything is interacting with everything. But if we can understand non-interacting particles, then we can think of interacting systems as a small perturbation from a non-interacting particle. And then we can start building up from there, right? So this is like our ground, is our starting point to really understand. And turns out non-interacting particles can also show lots of crazy behavior, like Bose-Einstein condensation. You don't need to have interactions for that. You can still have all sorts of crazy behavior. So we have these non-interacting particles, and N of them. Okay. So what we are trying to do, we are trying to do this first part today. We are trying to count omega NVE, the number of microstates for this. So in order to describe these non-interacting particles in phase space, I need to use variables R1, R2, R3n, right? Because it's in a cubic box, it's in Euclidean space, X, Y, Z coordinate. So we have 3 coordinates for each particle. So R1 to R3n and P1 till P3n. So it looks something like this, where you have R. This R is actually 3n dimensional, R1, R2 to R3n. And this P is also 3n dimensional, P1, P2 till P3n. And you know, it can exist here, it can exist here, it can exist here, it can exist here, blah, blah. We want to count the number of microstates that this system can take, omega. Given that this thing has number of particles n, it is in a box of volume V, and its energy lies between E minus delta E and E. So we want to count the volume in phase space that corresponds to this. How should I proceed? Go ahead.
Sum up all the kinetic energies of the particles, probably don't interact all the and ensure that it goes into.
So you have the right idea, but let's proceed systematically. So firstly, when I have to count volume in a certain space or area in a certain space, what calculus operation would you use for it? Integral, right? Area or volume is basically integral. It's not differential, it's an integral. So it's going to be integral in a very high dimensional space where I will go from dr1, dr3n, dp1, dp3n. If I did this integral over all possible momentum values and all possible r values, what will be the value of this integral? Infinity or zero? Is it even or odd? There is nothing. The integrand is 1, right? So it will be infinity. It will just sum up everything, but we don't have to do it for all possible values. This is where what Alex was saying comes in. This integral is restricted. So it's a 6n-dimensional integral. It's a 6n-dimensional integral restricted with volume V. So the values of R, the coordinates cannot be such that, for example, they are lying outside the box. This is not allowed, right? They have to be inside the box. So we have to think about that. And that's not the only thing. We also have to think about and energy. And this is where, again, what Alex was saying, this is going to be purely kinetic energy. Why? Because the particles are not interacting. There is no potential energy. Potential energy comes from interaction. Yes, you might say, well, what if they touch the side of the box? Then there is a potential energy. But right, it's a big enough box, so let's not worry about that. For now, I will just write down energy. Energy in E minus delta E to E. So it's going to be a messy integral, and we have to proceed carefully. What should we do next? Which ones and why? Why can we do that?
Because we don't have potential energy.
Yeah. So in this case, this integral can be written as dr1 dr3n and a separate 3n dimensional integral that is dp1 to dp3n. Kind of looks the same, but we have done something hugely different, right? Instead of a 6n dimensional integral, we have a product of two 3n dimensional integrals. So, oh, there's one. We were all missing it. So if you have, this is as complicated as doing a 1D integral versus doing a 2D integral, right? 2D integrals are messy. But if you could separate a 2D integral into a product of two 1D integrals, then it's way easier, right? A 3D integral is terrible. If you could separate it into a product of three 1D integrals, it's going to be much easier. So we have taken a 6n dimensional integral. So yeah, for those who came late, we are trying to calculate the volume in phase space that can be occupied by n particles in a box of volume V. The box volume, one moment, is different from phase space volume. And these particles are non-interacting. They don't have any potential energy. They have only kinetic energy. Go ahead.
Because the box shape is fixed, so it's clear, or you can separate it further.
Yeah, so that's what we are going to do next. So now that we have separated it, we can do one more thing. We can actually write down the value of this one. Every integral here is simply v to the power 1 by 3. Every integral corresponds to one coordinate, right? And if it's a cubic box, every coordinate is v to the power 1 by 3. Every axis is v to the power 1 by 3. This one is also v to the power 1 by 3, right? So each of these integrals is v to the power 1 by 3, right? So in total, this thing is, and how many of those do you have? 3n. So in total, this thing is v to the power n. So the first part, the first integral is v to the power n. The second integral is the messy one. We'll get to that in a moment. Okay. So this thing is why could we do this? Because there is nothing that depends here. The contribution of the position is trivial. There is nothing going on. Every particle is just happily moving around. You know, the way to think about it is, I don't know, Kinjal is just diffusing in this room. He can diffuse in any direction, and I don't know, Nick is also diffusing in this room in any direction. He does not care which is x, which is y, which is z. Further, he does not care that Kinjal is also diffusing, right? So every integral for every particle is basically the same, v to the power 1/3. And you have 3n of those, so you get v to the power n, right? dp1, dp3n. So I will write this down on the next page, this final last formula, and then we'll start from there. So we have omega is equal to v to the power 3n integral dp1. Is there a reason everyone is late?
Is it just deep to the end?
Huh?
Is it deep?
Oh yeah. Okay, I'll recap, Jared. So we are calculating the number of microstates for n independent particles in a box. See, everyone is late today. What's going on? Come on, man, don't be so late. I mean,
Yeah.
there was like some heavy grading or something. I don't know. So we have n particles in a box of volume V. They are not talking to each other. They're just happily moving around, and we want to calculate what is their number of microstates. So the number of microstates is an integral. Number of microstates is counting volume in phase space. So it's an integral in 6-dimensional space. The position part is trivial. Every coordinate is v to the power 1/3. So we get v to the power n. And now we have to worry about the momentum part. So that's going to be a bit tricky. So this integral is energy in the range E minus delta E to E. So now we have to think carefully. What is the total energy of n interacting particles? It is, in physics, it is known as the Hamiltonian. So the Hamiltonian, which is denoted H, it is not to be confused with enthalpy, and I cannot really help it that enthalpy is H and Hamiltonian is also H. It will become clear from the context. Hamiltonian for this system is going to be a sum of the potential energy, which depends only on R, the position coordinates, and sum of the kinetic energy, which depends only on momentum, right? What is the potential energy for non-interacting systems? 0. They are not talking to each other, right? It's nothing. It's only kinetic energy. Plus K of P. And that is not 0. They are moving around. So we have to calculate K of P. What is K? We know the momentum of every particle, right? It's P1, P2, and P3, and we know all the components. So this is oh, by the way, one student is on Zoom currently because Michaela tested positive for COVID. So this is something which is, if you have any reason, like you're going to conference or something, you can join the class on Zoom. I know, I don't care. It's okay if you are participating, but don't misuse the policy. And furthermore, let me know in advance. Okay. 3n squared by 2m. So this is 1/2m summation pi square by 2m I is equal to 1 to 3n. So this is the kinetic energy. And what are we saying now? We are saying, oh yeah. So what we are saying now is that this quantity has to lie between E minus delta E and E. So now you can see something is starting to emerge. We are calculating an integral in 3n dimensional space where the sum of squares of each 3n coordinate is restricted in a tight range. Okay, so let's try to see how we can do this calculation. So there is no R here, there is only P. Let's try to draw this space. It's going to look something like a bunch of axes. And this one is, let's say, P1, P2, P3. So we have lots and lots of axes like this, okay? 3n coordinates corresponding to each. So let's say this one is P3, this one is P4, this one is P5, and we have many, many more, right? We have 3n of these. So I want us to visualize this constraint. How will it look like in the figure that I drew below? Imagine if there were only 2 coordinates, okay? Imagine if there was only one particle. Again, I will go back to Nick. Imagine it's Nick diffusing in a 2D space, okay? So now Nick has only 2 coordinates here, P1 and P2. So Nick, how would that look like? I have coordinates P1 and P2. And I'm saying that now you should be E minus delta E less than equal to P1 square by 2m plus P2 square by 2m less than equal to E. This is the area I want to plot in P1, P2 space. How should it look like? It's like a circle. It's not an ellipse now, right? Because the mass is constant. It's not just a circle though. It's the difference between 2 circles, right? So this one corresponds to an outer circle, while this one corresponds to an inner circle, just slightly smaller radius, right? That is the whole idea. And that's the same thing you're doing in higher dimensional space. It's just a higher dimensional sphere. There is no fundamental difference. So we will have an inner circle that looks like this, and we will have an outer circle that looks like this. And it's, when I say circle, I really mean a sphere. And when I say a sphere, I mean a 3-dimensional sphere. Okay, so it's very, very high dimensional. And this quantity to which this integral is restricted is the part in between these 2 spheres or circles or whatever you want to call it. Okay, that's what we need to calculate. If we can calculate the integral over this part, we will be set. Okay, how should we do that? Well, the volume of this red strip let's say that the radius of the outer sphere is R, and that the radius of the inner sphere is R minus S. Okay, S is a small value. S is related to delta E. It's not quite delta E, right? It's related to delta E. So what is the volume of a 3n dimensional sphere with radius R? Does anyone know? How should it depend on R? Huh? Cubed, it's n dimensional, so it will be 3n, right? Does that make sense? I'm being a bit approximate here. So this is going to look something like some constant multiplied by R to the power 3n, right? It makes sense. If n is equal to 1, it's R cubed, right? Minus the same constant R minus S to the power 3n. Okay, and I'm being mathematically a bit, not too sloppy, a little bit. You can do the calculation and see that the constants are the same, nothing changes. This is what we need to calculate. If we can calculate this, it will be the volume of the microstate corresponding to this integral that we have written over here. That's what we need to calculate. The good news is we are not going to calculate the whole thing. We want to basically show a few things. What we want to show is that this thing does not depend on S, because S is the only thing here that depends on delta E, right? Delta E is what decides S and vice versa. There is nothing else. So let's work with this. But let me give you intuitive proof first for what's going to happen. So what we are doing here, so just like we drew this in 2D and now we are talking about 3n dimensional, right? So let's try to think of it systematically. So let's make a table where one column is dimension, the second column is area, the third column is volume, and this is ratio of area by volume. So in 2 dimensions, the area is 2 pi r and the volume is pi r square, right? So what is area by volume? That is going to be 2 pi r by pi r square is equal to 2 by r, right? Let's go to 3 dimensions. What is area? Anyone remembers? And what is volume? 4/3 pi r cube. Let's take the ratio of area by volume. 4 pi r square by 4 by 3 pi r cube. 4 cancel, pi by cancel. Something happened. Aha, it's almost a theorem is emerging. See what's going on here? You had 2 dimension, you had 2 by r. You had 3 dimension, you had 3 by r. For the same radius, which comes from delta E. So the point here is, and this is intuitive, okay, as n tends to infinity, area by volume tends to 1 because r keeps increasing, the numerator also keeps increasing. You know, again, it's intuitive. You look at it more mathematically, but you can see what's happening over here. So basically, when you are in a circle, a lot of stuff is still happening on the surface. As you go to a sphere, the amount of stuff that is, happening on the surface increases. As you go to higher dimensions, that stuff increases even more, which is kind of counterintuitive. That's how it works.
There is a problem with units.
It's intuitive, man. Don't get depressed. It's intuitive. I will do the mathematical part now. Okay. This is just to give you a sense of what's going on. Absolutely. Absolutely. Yeah.
So if some of the momentums are 0,
Yeah.
that wouldn't have all the stuff on the surface, all the density on the surface. Some of it would be in the middle where it hits 0.
Sure.
Do we even need to account for those? Because momentum is 0. They're not really contributing anything. Or if they're close to 0.
Yeah, but that's exactly what that is this point. This is where P1 is, P2 is 0. That's exactly what it is, right? So you're correct. So what you are thinking, if one of them is 0, maybe that goes well inside the sphere. But no, actually, that's still on the surface, right? That's why I drew the 2D one. Okay. So that's just the intuitive proof. If you like it, that's great. If not, that's fine. Let's proceed further. Let's look at it mathematically. So we wrote down Vs is equal to C r to the power 3n minus C r minus s to the power 3n, where C is some constant. I don't know what it is. It is whatever it is. You can, if you go and do a Google search, you will find exact mathematical calculations of these things. People have done it very, very carefully. So let's look at this one. So this is, what is this once again? This is our omega NVE. This is number of microstates with number n, volume V, and energy E minus delta E to E. So we have to do a couple of things. First thing, we have to calculate the value of S. Okay. So how do we do that? We have E minus delta E. Again, going back to the 2D, the one particle in 2D example, P1 square plus P2 square by 2m less than equal to E. So in 2D, what is the value of R, the radius of the outer sphere? It's easy. This is the equation of a circle, right? If the equation of a circle is x squared plus y squared is equal to c squared, what is the radius? C. So in this case, what is the radius? Square root of 2em, right? And for the inner circle, what is the radius? R minus s is equal to square root of 2 E minus delta E m. Will this change with the number of dimensions? It will stay the same. it's still, it's instead of a circle, you have a sphere, you know, it's the radius stays the same for higher dimensions. So we have this value. Now let's go back to, I should start numbering equations. Equation number 1. And so equation number 1, let me write this down here. So equation number 1 can be written as C r to the power 3n 1 minus s by r to the power 3n. This is exact. I have not made any approximation, right? I have just taken the r to the power 3n out and divided everything by it, right? Now I'll start making approximations. So let me write down this down on the next page. So we have Vs is equal to C r to the power 3n 1 minus s by r to the power 3n 1. This is equation number 2. So what approximations can we make in this? This is exact.
S over R is small,
Why?
because S is a very small number, or it's just a small subtraction.
So s over r is going to be positive, first of all, right? It's a radius. And it's going to be a much smaller number, okay, than 1. I'm not saying how much exactly, but something much smaller than 1, okay?
But you said that it does not depend on S, right?
What does not depend on s?
So the number of microsteps will.
Yeah, I know. So yeah, Kinjal is absolutely correct. Kinjal is saying, why are you saying that? Because you are going to prove that it does not depend on delta E. I'll come back to that, okay? So my claim that it does not depend on delta E has to be changed ever so slightly, which means that as long as you don't make delta E equal to E, then you will be in problem, okay? So you can have a huge range of delta E values. We will get that in a moment, okay? So for now, I'm claiming something which almost sounds opposite, because I was saying, I don't care about value of S. I don't care about value of delta E, right? But I'm saying, no, I care as long as it is small. How small does not matter, okay? That's the point. So if 0 less than S by R less than 1, then what can we approximate Vs as? This becomes C to the power 3n. Anyone recognizes what I can do here? 1 minus x to the power k when x is small. It's a hard one to remember, but it's actually e to the power minus 3ns by r. Right? And if you remember that this comes from 1 plus x squared and things like that. Okay. So you can just stop right there. So this is approximate. Equation 2 was exact. Equation 3 is approximate. And yes, we have assumed that s by r is a small value. It's not close to 1. It's smaller than 1, but it's some small value. So that's what, yeah, go ahead.
In equation 2, you had R order 3n, and you substituted only the internal brackets in the exponent.
Yeah, that's correct. That is the exponential approximation. That's correct. Yeah.
No, but where does the one on the outside of the bracket go? Because in the equation 2, you have CR to the 3n.
Oh yeah. I never did that. Now you have me on video. Okay, happy now? Sorry. So we have CR to the power 3n multiplied by this thing. Now, so this was our assumption 1. We can make another assumption. What can that one be? Thermodynamic limit. What happens to n in thermodynamic limit? It goes to infinity, right? We have very, very large number of particles. So now we can say that n tends to infinity. Now let's pay attention. So we have minus 3s by r to the power n, right? This thing is a positive or a negative number? It's a positive number. Is it larger than 1 or smaller than 1? It's smaller than 1, and does not depend how much smaller than 1, right? It could be 0.999, doesn't matter. If it's smaller than 1 and n goes to infinity, what will happen to this thing? It will go to 0, right? 0.99 multiplied by itself infinitely many times is going to take you to 0. This thing goes to 0. So what are we left with? We are left with Vs CR to the power 3n. And that's what we were trying to prove. Yeah, right?
What if S goes to 0?
If S goes to 0, then I think you can mathematically prove that the limit is still 0. N will win at some point because it's thermodynamic limit. Okay? Yeah, go ahead.
If S was approaching 0, our first,
But still it's less than
Assumption.
1, right?
It's still less than 1. Yeah.
yeah, but if S was about 0, you would say that the volume would be 0, because you would have 1 minus 1. In equation 2.
In equation 2, but that's why you have to keep this thing in mind. This thing will predominantly go to 0, the full thing, and it's the power of n in the numerator that takes care of it. So there was a bit of math, but let me try to summarize this, what we did over here, okay? And if this proof confused you, don't worry, this is more algebra than we normally have in this course, but the main method, well, slightly more algebra, not that much more. But the main method here is, the main idea here is that if n tends to infinity and S by R is much smaller than 1, and I want to revisit this because what was the value of S? S was something related to square root of energy, right? Square root of delta E. So notice that you're saying that this is related to some function which depends on delta E divided by E, right? S by R is related to delta E divided by E. As long as this thing is much smaller than 1 and the number of particles goes to infinity, the exact value of this thing does not matter. Okay, and it becomes, so going back to your point, Kinjal, the dependence on how relaxed you can be on S becomes weaker and weaker and weaker and weaker as n becomes larger and larger and larger. That's the point here, right? So if n is small, then you still have to be careful. You can't do too much. But as n becomes larger and larger in this high dimensional space, we can think of it this way, that when we draw a sphere in our high dimensional space, whether the thing is here or whether it's here, that does not matter. If you bring it over here, then of course it will start to matter because this criteria will start to break down. Okay. In other words, we have just shown that omega NVE is independent of choice of delta E as long as delta E by E is much smaller than 1. So you might say, oh, that is weak. You said it's going to not depend at all. But think about it. In thermodynamic limit, what happens to E? In thermodynamic limit, what happens to N? Goes to infinity. So what happens to E? Goes to infinity. So how hard it is to find a delta E that is much smaller than infinity, right? That's the whole point here, right? 1 kilojoule, 2 kilojoule, 5 kilojoule, 20 kilojoule, 50 kilojoule, 1000 kilojoule, 1 million kilojoule, you're still going to be fine. So it's really thermodynamic limit, and that's why what we are showing here. So this is quite powerful, and we don't have to dangle this delta E, otherwise we would be in trouble. So this was your first example of how to calculate microstates. Most of the time it will be simpler, but every once in a while it will involve integrals like this. And again, remember, microstate is the volume, number of microstates is the volume in phase space consistent with total number of particles n, volume V, and energy E. And I will give homework problem probably next week where you will do this in a few problems and try to get the sense of how it really works. Any questions? Yeah. Oh yeah. Well, no, not always. We will always check that the results make sense in thermodynamic limit. So what I'm going to do, if it was thermodynamic limit, then why we should not be talking about NVT, right? N goes to infinity.
You should not be talking about stagnant.
Yeah, exactly. So StatMech is something which, yeah, thermodynamic limit is the limit of StatMech. We will derive formula. Canonical ensemble will make it clear. You will see fluctuations, things like that. For example, yeah, it'll become clear. So thermodynamic limit is something we always have to check. It does not always apply, but we have to check what happens. So at this point, what have we done? Let's do a brief recap of microcanonical ensemble. So Chandler's book, by the way, is somewhat notorious because it does like microcanonical, canonical, and grand canonical in like half a chapter. And then says, okay, that's done. That's a terrible way of teaching it. It takes a lot of time to go through it. So we are working through that chapter of Chandler very, very slowly. Okay. So what have we done so far? We have talked about isolated system. So just a brief recap, which means constant n volume energy. It has number of microstates, omega nVe. If we have this, then the probability of a given microstate is going to be this value. If the energy in that microstate is E, the number of particles in that microstate is N, and volume of that microstate is V. And now I'm not going to write down here if the energy is between E and delta E, right? Because it does not matter. And 0 otherwise. This was our definition of microcanonical ensemble. This thing here is known as the microcanonical partition function. Microcanonical. Many books do not even use this name, but I like to call it that way. So it's microcanonical partition function. Our connection with thermodynamics comes with entropy. S is equal to KB, natural log of omega nVe. This is Boltzmann entropy. So going back to what Alex said, are we always in thermodynamic limit? No, we are not. However, if you want to use a microcanonical ensemble and calculate entropy out of it, you have to go into thermodynamic limit. Otherwise, the entropy does not make sense. Otherwise, your entropy will fluctuate. And thermodynamics told us it's a state function. Why should it be fluctuating, right? And from this, we saw our way to get out all sorts of different thermodynamic things, right? We looked at dE is equal to, and if you forget how to get anything from StatMech to thermodynamics, always start with this formula, which you should never forget. D is equal to TdS minus PdV plus mu dN. From this, you can manipulate and get all sorts of things. For example, temperature. So this can be rewritten as TdS is equal to dE plus PdV minus mu dN, or stay consistent. ds is equal to 1 by T dE plus P by T dV minus mu by T dN, or 1 by T is equal to partial S by partial E at constant NV. This we knew from thermo, but now we can say that this means that 1 by T is equal to KB partial ln omega by partial E at constant NV. And we bring this KB here to the denominator, and we call 1 over KT, 1 over KBT as beta, the inverse temperature. So beta is equal to partial N omega by partial E at constant NV. So this is the inverse temperature, which we'll be using a lot. And we could derive other things also out of it. We haven't really seen the use for it. You will see it in homework problems. And often, thermodynamics is all about picking the right ensemble. I have a story for you here. It's a kind of a, I won't call it warning story, but it's a true story. 4 years ago, when I was teaching this course, I gave a in-class exam, a take-home midterm or something. And there was one problem which could be solved in 2 different ways. It could be solved using canonical ensemble, or it could be solved using microcanonical ensemble. One way was obvious how to proceed. It was very messy algebraically. The other way was like, aha, so elegant, and you could get the answer in 2 ways. 6 students happened to have the second way of answer. It turns out they had not followed the exam property, so exam policy. And in this case, the 6 students eventually confessed that they had cheated and stuff like that, and it became a whole mess. So in thermodynamics, first of all, don't cheat. Everything will take home, follow the rules. I mean, I'm making open internet anyway, so but don't just copy from each other, because then what's the point, you know? And if you copy, I will probably catch you. And then it's not going to be fun for anyone, okay? And sometimes, so put a lot of thought into thinking which ensemble to take. And every problem can actually be solved with any ensemble, but the methods will be complicated. Because as we will see later, all ensembles are Laplace transforms of each other. But you know, it will be, instead of doing this, you will be doing something like this. And it will make me suspicious. That's the story. It happened like 4 or 5 years ago. So let's proceed further. So we have recapped microcanonical ensemble. It is everything to know about the microcanonical ensemble is captured in the microcanonical partition function. From that, you can get thermodynamics if you assume thermodynamic limit. But an isolated system is kind of boring and useless, right? You can't do anything. It's stuck. We want to go one step further, right? We want to think about systems with which we can do practical experiments. So just like we are following the pattern, just like we did in 684, right? NVE, yeah, it's okay. But also energy is hard to measure. Temperature is easier to measure, right? You just use a temperature and it tells thermometer and it tells you what's going on. So in practice, NVT are better control parameters. We will go one step further. Instead of V, we will have pressure, which is even nicer perhaps. But I think volume is also okay. You can measure the volume of something. So NVT ensemble tends to be quite useful. And such an ensemble is known as the canonical ensemble. And just like microcanonical ensemble was called NVE ensemble, I will often just call it NVT ensemble. Okay, so what do I mean by that? Let me define it. A canonical ensemble is assembly of, maybe this desk can go up. This is like terrible. There used to be a chair here. You remember, like when we started last semester? It's a great chair. Now it's gone. Huh. Assembly of all microstates. An ensemble is always an assembly of microstates, right? That's something which is always true. But now we have additional constraints. Earlier, it was assembly of microcanonical ensemble was assembly of all microstates consistent with fixed number, fixed volume, fixed energy, right? Now it is assembly of all microstates consistent with fixed number, fixed volume, but energy can fluctuate. It fluctuates in a very special manner. The system, which can take many different microstates, is kept in thermal equilibrium by being in contact with a, and this term will show up again and again, we call it a bath, which immediately conjures up memories of like taking, you know, I don't know, relaxing in a bath. No, it's not that type of bath. Is it? No, not really. Bath, or often it's called reservoir. Okay. The idea being something way bigger than the system. That's what the image that is intended to conjure. Oh yeah, Vedant is not here. That's what I was missing under the vacancy. So how does it look like? We have a system. Oh, that looks like a, you know, for no reason, like a slanted thing. It's just a box. And this thing has volume constant V, number of particles constant N, but the energy can go in or out. It's at equilibrium though. It's not that there is a constant overall flux of energy in one direction, okay? Some energy is going in, some energy is going out. it's balanced on, and we know the balance for this is temperature being constant, right? So we can talk about temperature T. What is the temperature of a system with microcanonical ensemble? There is no temperature, we cannot measure it. Well, is there? We defined it. We can calculate it, right? It's not that obvious. We just wrote it down. You can actually calculate the temperature, right? By doing this calculation, but it's not, I said no temperature because the temperature is not a control variable. You cannot just control it. You see, in microcanonical ensemble, the temperature is derived from the key thing, the microcanonical partition function. Here, the temperature is imposed. It's something you're imposing. That is the main idea. So in any ensemble, you can calculate any property that you want. You can calculate E in canonical ensemble, and you can calculate T in microcanonical ensemble. But the question is, one moment. T is derived in microcanonical and E is derived in canonical. Go ahead.
So, but this all these quantities will make a physical sense only in the
You will see all that in great detail. So in order to study this, what do we want to do now? We again want to calculate the probability of a given microstate of a system, right? So for microcanonical ensemble, we saw that the probability for a given microstate was 1 over omega NVE. Here we will see that the probability of a given microstate is e to the power minus E nu by KBT. And I wrote proportional because probabilities need to sum up to 1, and that's going to play a huge role, okay, in a moment. This is known as Boltzmann probability in some book, but I just call it the canonical ensemble probability, okay? It can also be written as, and you can see why we introduced the beta term, because K subscript BT shows up so many times, and especially in the denominator. So when JP tries to send his homework, he uses LaTeX for his homework. Who else uses LaTeX here for homework? Only JP. He will have a hard time because he will have to use slash, frac, blah, 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 all those things, right? So JP can simply write now e to the power minus beta. Huh? No. Great. A semester too late. Well, you picked up life skills, you know. Okay, so this is what we are going to show, that the probability of microstate is going to be all. So in the microcanonical ensemble, there was only one energy. Now we have a whole distribution of energies, and you will see that this distribution actually goes as it dies down exponentially. Before I go into the proof, I want to show you why this matters or not. So if you think about, I want you to think about, well, actually we can do it in one graph. Think about omega as a function of E for a microcanonical partition function. How did that behave? It was steeply increasing, right? Not like a log, but steeply increasing. Something like this. How does this one behave? It's steeply decreasing. Oh, what did I do? So that's omega. And if I draw e to the power minus P nu, behaves like this. So if I think about P nu multiplied by omega, how's that going to look like? Huh? Any ideas? We will come back to this later. Huh? Caution, why? He just remembers. Memory is not an answer. Can you explain why?
Because at one end you have 0 times.
Yeah, it depends on how these things go to 0, how quickly they are going, right? But you will show soon. Chandler actually has this as an exercise problem. Their product is going to look something like this. And we will revisit this later. as to later we will revisit why this makes a sense. Okay, once we have done canonical ensemble. And as the system size becomes larger and larger, as the Gaussian becomes closer and closer to a delta function. Okay, we'll come back to this later. But first, let's try to prove that P nu is e to the power minus beta E nu. So in order to do that, we have to visualize. So what did he say? This is a system that can exchange energy with the surroundings, right? So let's make one copy of the system where the number is n, volume is v, and let's say it has some energy E1, okay? And it's in this big ocean, bath, reservoir, whatever you want to call it. Let's make another copy of the system where once again, number and volume are fixed, but now the energy is E2. Let's make a third copy of the system where NV and this is E3, so on and so forth. And that's what we really want to calculate now is that at equilibrium, what is the probability of finding one such copy of the system, right? As the energy becomes higher and higher, the probability, as I said, we will show, decreases exponentially. You'll still find it, but the probability will be smaller. And all of this, each such copy is embedded in a heat bath. So it can exchange energy with the bath. Here we have certainly made assumption of something. We have used something that we showed in the very beginning. We have used ergodicity, right? Because if we really had to do this correct, I would not make n copies of the system. I would study this system at n different time instants, right? But here I'm saying, no, instead of that, just make n copies, right? So we are assuming ergodicity here. But then, does anyone know, has anyone here read Brief History of Time by Stephen Hawking? He talks about an example in the preface. You remember which one? He says, well, the world is on a tortoise, and the tortoise is on a tortoise, and then that tortoise is on a tortoise, and that tortoise is on a tortoise, and what happens after that? He tries to motivate. I don't know why he talks about the tortoise thing, but that's how he starts the book. So the question here is, what happens to the heat bath? What's outside the heat bath? So outside the heat bath, there is nothing, okay? The story ends. So this is thermally insulated. In other words, system plus bath is equal to micro canonical ensemble. Okay, that's our starting assumption. The second assumption here is that the system is very, very tiny related to the bath. This is the two things we will proceed with in order to derive what we said next, what the P nu is equal to e to the power minus beta E nu. As I mentioned, if you go and read Macquarie's book, he doesn't do it this way. He derives this by assuming maximum entropy framework, which is one way. So you have to go somewhere?
Yeah.
Yeah, I'm going to stop here, so don't worry. Yeah, knew you have to go. Where do you have to go?
The lunch with the interview candidate.
Oh yeah, well, yeah, go impress her. So I want you to read the derivation after this in Chandler's chapter 2. He talks about it. He talks about it very, very quickly, typical Chandler style. I will do it in great detail. So Chandler, when I was a postdoc, I first met Chandler, and the first time I met him, he comes to me and he used to have a very nasal voice. So Soiman is working on this problem of getting like dynamics from metadynamics, and he comes to me like, you are the guy getting dynamics from metadynamics, and then he like grilled me for 2.5 hours non-stop. So I have memories of him. Anyway, so read this, and next time we will work on this derivation. We will use these two facts to derive that P nu is equal to e to the power minus beta E nu. And so, yeah, we have worked till somewhere over here. This we will do next class. And I'm going to have a homework some point next week, which will go over all the concepts of microcanonical ensemble. Okay, good. So see you on Tuesday. Bye, Michaela.
Thank you.